All right, thanks for having me. This is a little bit of a technical talk. I hope that's okay. So I've been working on this open source project for the last what is it, 2018? So a little over 3 years, and I spent about a year before that kind of thinking about what kind of project might solve some of the problems that Apache Arrow solves, and so I've been working on these problems for a pretty long time. So some of you may know me from my work in the Python community. I created the Pandas project, which a lot of people use. That was a little over 10 years ago. Became an open source project at the end of 2009. And it didn't start becoming popular until maybe 2011 or 2012. I wrote the Python for Data Analysis book, which is now in its second edition. There's lots of translations, so you can buy it in lots of different languages. And I've gotten involved in a number of other open source projects, in particular in the big data community. So I had a startup for a couple of years called Datapad that was acquired by Cloudera at the end of 2014, and so I arrived at Cloudera with the mandate to essentially bridge the gap between Python data science tools and the big data world. And the Arrow project is something that, for me, that I became inspired about as a result of wanting to make the data science ecosystem more compatible with the big data world. So I've worked on some other projects. Maybe some of you have heard of the IBIS project. If you have not, I suggest that you check it out. So it makes it makes it so that you don't ever have to write SQL again, but you can still access all of the power that you have in modern analytic SQL databases from the comforts of writing Python code. I've also done some work on the stats models project, which helped bring traditional statistics to Python. Earlier this year, I founded a new organization, a nonprofit open source development group called Ursa Labs, and one of the objectives of Ursa Labs is to build a team of people that are focused on building the Arrow open source project, and in particular to build shared infrastructure libraries for data science that are powered by Arrow. We are working with different corporations to fund the lab. So to start out, like I've known Hadley Wickham in the R community for a long time, so I wanted to build a close partnership with the R programming community so that we can focus on building high-quality software that can be used both in the Python world as well as the R world and beyond. We're also collaborating with the Ruby community lately, so we're going to start having some more data science tools in Ruby, if you can believe it. So that's very exciting. So our current partners and sponsors for Ursa Labs right now. So I'm working very closely with RStudio to deal with kind of the administrative side of building a team of software engineers. Two Sigma, where I used to work, is also funding. They're a financial firm in New York City. They're funding the initiative, and just this month, NVIDIA has signed on as a sponsor of the lab as part of their Rapids GPU-powered analytics initiative, which is all powered by Arrow. So this talk is, I think I'm going to talk about particular things that we're building, but really, if you take a step back, what's the big picture here? The data systems have grown very fragmented over the years, in part because a lot of open source developers work in isolation. You have a problem or a set of problems that are right in front of you. You work in a particular programming language in a particular ecosystem, and you build some software that solves the problems that you have. Maybe you turn that into an open source project, And so a lot of open source projects develop without a great deal of collaboration beyond the walls of a particular small part of the ecosystem. And to build open standards and to build shared technology that can be used by multiple communities is really difficult. If you do manage to build an open standard, whether it's like a standard file format or a standard protocol, something like XML or HTML, it requires a lot of work to get everybody to agree. But when you do that, you make the world a lot simpler, because now you can make certain assumptions in your system architecture. It's like, oh, well, we're going to use this open standard to solve this part of the system, so you don't have to invent some custom thing. You can use something that is standardized and adopted. So by adopting open standards, you can make the world a lot less fragmented. You can make systems more interoperable. And for me, open standards that have to do with data are particularly important, because you can reuse data that's coming from other systems without nearly such a high cost. And you can also reuse code and libraries of algorithms, because algorithms are implemented specifically targeting particular data formats. So if you can reuse code and reuse algorithms, you can be a lot more productive. So you're probably familiar with some of the open standards that we have out there. So things like XML and JSON. SQL, it was tried to be an open standard, and there is SQL 99, but in practice, every SQL database implements a slightly different variant of SQL, and they call their functions different things. There's a different variety of different storage formats, binary storage formats, which are used in different communities. So if you do data warehousing in the big data ecosystem, or you use Spark, you're probably familiar with the Parquet format, or more people are using, more and more people are using the Orca format. Now that Cloudera and Hortonworks are the same company, maybe they can do something about this sort of split between Orc and Parquet, because it used to be, it's like, oh, they were developed by, the Capulets and the Montagues, and now it's just one family. So we'll see what happens there. We have standards in communication protocols, so remote procedure call systems like protocol buffers, Thrift, Avro, kind of all invented to solve the problem of arbitrary structured data serialization, so you can communicate data, payloads, and commands between clients and servers. Some people think that CSV files are an open standard, but they're not, so don't let anyone convince you otherwise. We don't have a lot of standards when it comes to data that is in memory. The best example of an open standard is the multi-dimensional array model, which is used in, I think originally came out of Fortran. So in the 70s and 80s, the way that Fortran arranges data in memory for working with ND arrays or tensors, depending on who you're talking with, they might call them tensors, they might be called ND arrays. But having that standard memory layout for strided multi-dimensional arrays has made it a lot simpler to build machine learning applications and just numerical computing in general. And so when people created NumPy and the precursors to NumPy in Python, so that was numeric and numarray, this was back in the 90s, they didn't have to really design a new memory format, because there was the one that was used by BLAS and LAPACK and Fortran. And so, by reusing that memory layout, you could reuse all of these decades worth of algorithms which operate against that standard. So you can reuse code, you can reuse data. You can also share data between processes or between different libraries in the same process without any copying. And I think that with something like NumPy, that ability to apply a multi-dimensional array view onto a block of memory is one of the things that makes the library really powerful. So you can reinterpret, you can give a multi-dimensional array interpretation to a block of arbitrary memory. When it comes to other kinds of in-memory data, so things like data frames. So if you use data frames in R or Python, or you have in-memory data inside a SQL query engine, there's really not not an open standard for tabular data, and the reasons for this are complex. I think in part it's because these systems developed with vastly different requirements. So some systems have the notion of tables, but they want the memory layout to be row-oriented. So Spark, for example, uses a row-oriented in-memory format for its tables inside Spark SQL. Some SQL databases have a columnar, kind of column-oriented layout. Some are row-oriented. But even within the data science world, where things generally are column-oriented, there's still a lot of variation in the way that the memory, the data is arranged in memory. So for example, in pandas, when you have strings in pandas are represented as NumPy arrays of Python objects. So each cell in a column in a pandas data frame is a Python string object that's in the Python object heap. And so if you had a bunch of string data in a pandas data frame, there's basically no way that you could expose that memory to an external consumer without also exposing the Python C API and a bunch of internals of Python. And so that makes interoperability very difficult. But these data frame projects are important because if you're thinking about doing machine learning or doing AI, like really that like a large fraction of data ends up passing through one of these data frame projects. Like you have to load data out of storage, do some data preparation, feature engineering, and a lot of that data will end up passing through one or more data frame libraries. So having really high quality software for this problem space is pretty important in making people productive doing doing data science and I guess what we're now calling AI. I guess you can call about anything AI now and get away with it. So things are fragmented. So one reason that I think that things have become very fragmented in the internals of these libraries. So one problem is that the back-end implementation of these projects is often very coupled to the front-end API. So the code that you write in Pandas exposes a lot of details of how Pandas itself is implemented, and the same is true of equivalent R libraries in a lot of cases. And so if you want to change something in the way that Pandas represents its data in memory, that would be disruptive to the front-end API. It's difficult to get different open source communities to collaborate, and some of that is cultural, some of it's just it's just a logistical issue. Like even sharing even a small library of code between, let's say, an R project and a Python project is very difficult, and there's not a lot of examples of that happening in practice. But it's a bit sad because if you're working in an environment where you have code written in multiple programming languages, and you want to move data from one environment to another, you have to pay a serialization cost to move data from point A to point B. And if you have some useful algorithms which are written for use in R, you often can't make use of that code in another environment without doing a significant amount of rewriting of code or building some like glue code to kind of bridge the worlds. So I'd experienced this pain for many years, and I decided to start doing what I can to make the world a little bit better in this way and a little bit less fragmented. So I got together with about 20 or 25 open source developers in 2015 to discuss the idea of developing an open standard for tabular data, for data frames effectively. And in particular, what I wanted to see personally happen was to see the database world, so people building big data systems and traditional database systems, begin to collaborate in a meaningful way with the data science community. And so if you think about like how many examples we've had where like somebody building a SQL query engine has built a piece of software which can be used in Python or R or a data science library, there's really not a lot of examples. And when you consider the amount of technology innovation that's happened in database systems in the last 20 years, very little of that work has made its way into the hands of people doing data science. So this project in part is about helping change that. So semantically, kind of what we're looking for is we have many different execution engines, many different storage systems. We'd like to provide a common medium for data access, data movement between applications, and provide kind of a point of collaboration between diverse systems. And so when I came to kind of collaborate with the big data, like the Hadoop ecosystem at the end of 2014, one of the things that filled me with dread was building data connectors into all of the different file formats and all of the different storage and execution systems. So I was collaborating with the Apache Impala team. It was still just Cloudera Impala back then, but we were looking at, okay, if we want to write custom operators for Impala, which is a SQL engine, in Python, what do we logistically have to do to make that happen? And one of the first things was we have to come up with a way to exchange data from the SQL engine into the Python world so that we can get access to it in pandas and then send the data back to Impala. So we needed to define a data protocol for moving data sets between either in memory or from one process to another. And so rather than build something, and I did build like a custom serialization format just for use in Python and Impala. And I had to kind of look at that. It's like, wait, why isn't there just a piece of off-the-shelf technology that solves this problem really well? Why am I having to invent a custom column-oriented data protocol to move data between these two systems? So if you're sort of thinking about this from the perspective of data science users or people working with data frames, so we have data frames, we call them data frames in different programming languages, but the data itself is not portable between environments. So the purpose of Arrow is to provide a portable data frame that can be moved easily between languages that allows us to easily share data and share code. If you're somebody who's worked on database systems, traditionally, database systems are very vertically integrated. So the only way that you, as a user, can interact with the database is by sending SQL queries into the database. So you're interacting with the front end of the database. But there's all these other components that are part of the. Let's see how this works here. Does this work? Okay. So whenever you send a SQL query, the SQL query is translated into a logical query plan. That goes through a further conversion from the logical query plan to the physical execution plan. And that's evaluated by the internal query engine of the database. That query engine has to operate against some in-memory data representation. So that might be some column-oriented in-memory data or some row-oriented in-memory data. That in-memory data is materialized through various I/O subsystems which might interact with if a database has its own native storage format. So if you're talking about like something like Postgres or kind of older databases, they have their own kind of custom storage. If you're talking about Impala or Hive or Presto or Drill, kind of modern SQL and Hadoop systems, their I/O systems are working against S3 or HDFS and materializing data out of open standard file formats like Parquet and Orc and Avro and so forth. So our goal with the Arrow project is to basically break apart, kind of deconstruct the analytic database, as we call it, to sort of look at each of these components in isolation and to offer a computational query engine, an in-memory storage layer that's language independent, and an I/O and data access, a set of libraries for I/O and data access. But these all have public APIs, so the idea is you can take what you need and use these components to build your data applications. The one thing that we aren't really interested in getting involved in is the design of front-end APIs. So it might be that we do offer some front ends to access the tools, for convenience. But I personally, having built a number of front end, data analysis libraries over the years, I intend to continue to do that personally. But I think a project like Apache Arrow, which is very much like a foundation of next generation data processing systems, doesn't really have any, in my opinion, doesn't have any business being prescriptive about what the front end should look like for accessing this technology. So that's up to the people building databases and building query engines and so forth. So here's your kind of deconstructed noodle soup. So the primary use cases that we're interested in the project. So if you're thinking like, let's try to make this a little bit more concrete. I think what I've been saying is pretty abstract. So one major area that affects the performance and scalability of systems is data access. So we'd like to be able to read and write the most commonly used storage formats, to be able to get, if you have data that's in Arrow format in memory, that you can write data out into various storage formats. You can read data in as efficiently as possible and in as many programming languages as possible. That you can efficiently interact with database protocols, so that would be ODBC, JDBC, the native database protocols like Postgres, MariaDB, which is formerly MySQL, TDS, which is Sybase, SQL Server, and there's other database protocols. So basically, we can push and pull data from storage as efficiently as possible. Within the world of Arrow, we're developing tools for sharing memory between processes. So if you have a large data set that you need to access between different processes at the same time, that you can materialize data in Arrow format in shared memory and then access that data in shared memory pages that are effectively on disk or in kind of virtual memory without having to do any copying between processes. We're also developing messaging framework for kind of remote procedure calls. So if you want to build custom data services, so these could be data microservices or really any kind of data service, you'd like to be able to offer a very fast port for pushing and pulling data sets. So you can think about kind of the RPC problem as being alternatives to other kinds of database protocols. So if you might be familiar with ODBC and JDBC, those are serialization-based database protocols. So databases convert to an intermediate representation, which is like the way that ODBC or JDBC puts data on the wire, and then the clients deserialize from the JDBC or ODBC wire format into wherever the data is going. So we would like to have Arrow on both the server and client, and move Arrow over the wire and have no serialization on either side. So lastly, we're building computational libraries to be the components that you would use to build Arrow native query engines. So that will involve kind of a mix of precompiled operator kernels. So if you're familiar with TensorFlow or kind of deep learning libraries, very similar kind of approach to building like a operator graph based query engine with a mix of code generation with LLVM and precompiled operators. So I've been talking at a very high level about all these things, but so I'm going to go into a little bit more detail about the Arrow format and some of the things that we're building in the project right now. So so one of the biggest parts of the project, it's become like a pretty big project, so much so that it's hard for me to keep track of all the components now. But one of the things that ties the room together is our column-oriented memory format. So you can think of this as being kind of language-independent data frames, or a way to represent runtime data in a columnar SQL engine. So it's optimized for for analytics. So it would be less suitable for building a row-by-row, like transactional database. So it's efficient for doing both scan workloads, so where you're reading data sequentially as well as random access. So when you have an Arrow table in memory, you can access any value in any column in constant time. And so if you're doing random access, it works very well. If you're just doing scan-based workloads, let's say you're doing aggregations or filters, the memory is arranged in a way that is very efficient for the CPU or efficient for the GPU. So one place where we've done some work to integrate Arrow and get some early performance benefits is inside Apache Spark. So one of my colleagues from Lee Jin from 2 Sigma, Brian Cutler from IBM, they worked together on this. And the idea is that Spark allows you to extend it with custom user-defined functions that you write in Python. So whenever you're using PySpark, you can use the Spark data frame API, which is effectively equivalent to writing SQL code with Python API calls, but you can also write custom Python functions and expose those as operators to Spark SQL. But the way that the data is serialized and moves to Python for evaluation is pretty inefficient. And also the execution model, the default execution model is row by row, and so you have one Python function call for each row in the data set, and that's also very slow. And so the idea is that we wanted to be able to write code that essentially the model is pandas data frames in, pandas data frames out. So you get the benefit of a kind of vectorized, kind of array-based execution. And we want to use Arrow for moving data over the wire. And so in a number of different use cases, we're able to get from a few times speed up through like over 100 times speed up in different kinds of custom operators. But when you see like what we're doing is, so Spark SQL streams. Let's see if this works here. So Spark SQL streams data through a socket. So this is the architecture of the way PySpark works. So it converts its internal data to Arrow format, sends it through a socket to the PySpark worker. That gets converted to a pandas data frame. The operator is evaluated, and then the data is streamed back to Spark through Arrow format. And so even though we have like 4 distinct serialization steps, because the interchange format itself is very efficient for both sides to work with, that even with like 4 different serialization steps, we're still able to get like a pretty significant performance speed up. So I think the really interesting thing in the future will be when both sides of the, if we have a distributed database or distributed data processing engine on the left, and a kind of a single process worker on the right, if they're both using the Arrow format on the left and right, then we don't have all that extra serialization, and so that's going to be significantly faster because there's no conversion at all required. Something we've just started building right now, so since I don't know, is anyone using gRPC in the room? A few people. So for messaging, so gRPC, as far as I can tell, is sort of taking over the world of RPC frameworks. So it's based on, it's created by Google, so it's Google's internal RPC library. It's heavily skewed towards protocol buffers. You can use other kinds of serialization, like you can embed your own serialization if you don't want to use protocol buffers. But the experience of using protocol buffers makes things really makes things really nice. And so what we wanted to do was to do a low-level integration between the Arrow libraries and the gRPC transport layer to make the movement of data from from server to client as efficient as possible. So essentially, kind of on the inside, in the inside of this library, we're writing Arrow tables directly onto the gRPC buffer that's about to be put on the wire, and then on the client side, when you receive a payload through gRPC, we're avoiding any additional deserialization or copying from the memory that gRPC allocates from or the gRPC reads off the socket, or however HTTP2 works. I think it uses TCP. So essentially, so a client, so there's different topologies you could use to set up your data services. So if you wanted to have a more scalable data service, you could have many data nodes which are able to provide fragments of a data set. And so a client would ask a planner node for essentially an access plan for a large data set. And maybe it turns out that the data set is split across 10 different data nodes. And then you could go and perform the get operations in parallel across all of those data nodes. And so within a single data node, when you make the get RPC into the data node, we're getting a stream of Arrow column batches through a gRPC stream. But we've done some low-level optimizations in gRPC so that even though this data is transported embedded in a protocol buffer, that we're avoiding any extra parsing or any memory copying or serialization on read. And so this has been really exciting to work on, because just on my laptop with a single thread and from server to client, like I'm able to move about 3 gigabytes per second, which for effectively a database protocol is more than an order of magnitude faster than anything else that you can pick up off the shelf and use. I mean, I think usually getting with serialization and everything, if you can get 300 megabytes per second in a database protocol, you're doing pretty well. But to get multiple gigabytes per second is it's just next level performance in data access. So, but this is all very generic, and so what I would like to see happen is to make it really easy for people to build custom data services. And so our RPC system, which is called Flight, is agnostic to the command layer. So you can define your own custom commands. If you want to define your commands using protocol buffers or Thrift or whatever you like, you can embed whatever kind of command in the RPCs. And so obviously a client needs to know what kind of server it's interacting with and what kind of commands it supports, but we don't really take any view on what you use to represent how you structure the queries that you're sending to servers. I'll skip this part. So anyway, so Arrow is a 3-year-old open source project. As you can probably guess from this talk, its scope is massive and incredibly ambitious. I need to update this slide. We now have some support for 11 programming languages. The 11th programming language is C#. So I'll insert a C# here. But the way that a lot of the implementations depend on the C++ library. So from C++ we get to C, from C we get to Ruby, from C++ we get to both Python and R and MATLAB. But we do have native implementations in JavaScript, Java, Go, and Rust as well. So the Go and Rust libraries are the most new, and so if there's any Go hackers in the room or Rust people who want to do some Rust programming, this is a great project for you if you like systems, of course. This is a great project for you to get involved with, because those projects are just getting off the ground, right now. The C++, Java, and JavaScript libraries are a lot more mature. So the way that we test the project is that we generate the binary protocol messages in each of the programming languages that support them, and then we make sure that all of the other libraries can read them. So if I generate a data set, like a binary Arrow data set in C++, I make sure that the C++ library can read that back and check that it's the same data, but also that the Java and JavaScript libraries can read it as well. So right now we have a 3x3 matrix of Java, C++, and JavaScript, and at some point that should grow to be, let's say, 6x6, because we need to add Go, Rust, and C# to the matrix. So another cool thing that's happening right now, there's a component that was just contributed to the Arrow project that was initially started by the Dremio Corporation. You know, Dremio is a kind of SQL-based kind of federated data access product, and it's written in Java, and they wanted to accelerate their SQL evaluation using LLVM. And so because we have a common memory representation for tabular data both in Java and C++, so they could build an LLVM compiler for SQL expressions, hand off data from Java into the kind of LLVM C++ side of things without doing any copying, evaluate a just-in-time compiled function kernel, and then hand the data back to Java without any copying. So I think it's always been the dream to be able to do free data interchange between the JVM and C++, and like we finally are able, to do it in a pretty exciting way. So this is also a big thing that's going on in the project, right now. Another project you may have heard of is the Ray machine learning framework. It's being built for a number of different machine learning applications, in particular reinforcement learning and real-time, real-time machine learning applications at the Berkeley RISE lab. So Ray's architecture is based around the idea of independent Python processes sharing the results of computation via shared memory. So they initially developed a system called Plasma, which manages large amounts of shared memory, which is used by a group of processes. And so they're able to serialize and complex data sets in shared memory and then read those in each of the worker processes with minimal effort. And so it's cool to see kind of a new machine learning framework that's built around this idea of free memory sharing between processes. And this would not be possible without all of this engineering that we've done to build up this kind of platform of kind of structured data access. Another thing that's happening, it's been rebranded. So NVIDIA has launched an effort called Rapids, which is essentially GPU-accelerated data science pipeline. So they're building a CUDA data frame library and a set of additional libraries which that go along with cuDNN and the other kind of CUDA deep learning libraries that NVIDIA has built. And so when it comes to feature engineering and data frame type analytics, I mean, everything is powered by Arrow. So it's great to see NVIDIA kind of buying in on this vision of kind of leaving data in place and having an open standard for data frames. So lots of contributors. I've got to update this slide. I think the number of logos has gotten a lot bigger. So it's a big project, but lots of exciting stuff on the horizon. Kind of as I'm kind of building a bigger team of engineers to work on the project, a lot of our work is into kind of scaling the development of what's become a much more complex project, making sure that it's easy to import and export data as efficiently as possible in the Arrow format. And really, our goal is to build a set of computational libraries which can be used as the basis of next generation data frame libraries and in general purpose next generation data processing systems. So tons and tons of work to do. kind of let you read up on this stuff on your own, all of the different data formats that we want to access. But it's certainly become my dream, rather than having kind of libraries like pandas be these full stack systems which are only available to Python programmers, that we can kind of re-architect things around common libraries which can be used in multiple programming languages and have a much larger community of developers working together to build these systems. So that's my talk. Yeah, kind of, I try not to overwhelm you with technical information, but there's tons of stuff here that you can dig into and find the parts of the project that are most interesting or relevant to you. And we'd love to have you involved in the open source project. It's a growing community, and we have a lot of exciting stuff to do over the coming years. Thanks.
Thank you so much, Wes. So let's just jump to the question straight away. What is Arrow's new Gandiva execution kernel? How Gandiva compares to the old Arrow engine? As users, we just got a newsletter that Dremio 3.0 just released with Arrow's Gandiva, boosting 10 times performance improvements. Is it true? How?
Well, we don't. Okay. Well, I can't show you my screen. It's fine. So we didn't have. So I guess the old Arrow engine would be. I think what they're comparing with is Dremio's all kind of native Java execution engine, and so the internals of Dremio. This is not really an Arrow thing, but the internals of Dremio are all Arrow-based, and the expression evaluation part of the system is interpreted and all written in Java. And so that kind of interpreted execution expression evaluator has been replaced in many places with the kind of just-in-time kind of LLVM compiled version. So that deals with like optimizations like operator fusion, elimination of temporaries, SIMD instructions, and so that's what's giving them that level of performance speed up. But Gandiva is part of Apache Arrow, and so we just recently, they donated the code base to the project, and so the work is now happening in the Arrow community, which is really exciting. Okay.
Thank you so much. What is the main use case for sharing raw data in memory between processes? What made you realize there's a need for it?
Okay. For me, the major use case was extending a database engine with custom code. So traditionally, database systems are uncomfortable exposing their runtime data representation. And so if you want to, let's say, extend a database with Python or extend a database with R, the data has to be translated out of the runtime into some intermediate representation for user-defined functions. And then that custom code is evaluated, and then the data is translated back. And so you're leaving a ton of performance on the table over what would be possible if you were coding directly against the runtime data representation. So the purpose of Arrow is to make database systems and data science systems comfortable exposing their internal data to the outside world and having a public API.
Thank you. Will Arrow become an alternative to Panda, or will they work together? Or more precisely, will Arrow's focus be on data storage or also deliver wrangling methods as Pandas has?
So to my point in the kind of earlier in the talk about Arrow being front-end agnostic, so Pandas is very much a end-user tool, so it's a front-end system. So I think Arrow can be used to improve some of the internals of Pandas. I'm pretty interested in building basically a kind of new Pandas-like library that is based around lazy evaluation and has like a query planner built in that's not eagerly evaluated like Pandas. I think it would be very difficult to retrofit Pandas with that type of functionality. So I think we'll see a mix of Arrow being used to accelerate Pandas and kind of new, kind of a new data frame project which can be used as a complement to Pandas. But that's kind of a multi-year project.
Thank you so much. I love it. The question was asked by biggest fan of Wes.
That's funny.
There's a true fan. But our time is up.
Yeah.
And I think we need to move on because, as I also mentioned to you, that there's a raffle happening at the MU stage, and also there's still a talk that will go on. So thank you, Wes, again a lot
Yeah. Thank
for
you.
being here.